Hi, my name is Diego Garcia, and I am a physics undergraduate from Cal Poly Pomona, and I will be presenting today on my research in simulating photonic cavities for quantum optics applications. So I've been working in Dr. Ma's lab group, and my project will be assisting one of the other lab members, whose name is Rogero, who has been working with K-space imaging, which is basically a mathematical transformation of the image that allows us to correlate spatial frequencies with certain properties of the object that we are imaging. K-space imaging is most well known as being used within the medical field for MRI imaging. However, it is also a useful tool for the imaging the structure and orientation of electrons within different molecules, which is the property that Rogero is using it for within his research. As an example, here's a figure on the right taken from a paper on using K-space to measure the orientation of electrons within the bonds of a molecule. Rogero has been using what's known as photonic cavities, which are essentially structures in which there is some form of cavity which allows for the trapping of light for a certain amount of time. The type of cavity that he has been using is known as a Fabry-Perot cavity, which is two small mirrors facing each other, of which are typically distributed Bragg reflectors, where there is a small gap of air in between the two mirrors that allows for the confinement of light based on the width of the gap. The measurement of performance of how well these cavities confine light is what's known as the quality factor, which is also referred to as a Q factor. We see that in these types of cavities that the highest order of magnitude that the Q factor has been measured at is on the scale of 10 to the fourth. Another type of cavity that is known to have the potential for having a much higher Q factor, which is on the scale of 10 to the seventh, is what's known as photonic crystals, which are basically semiconductors with holes bored into them, in which the holes are bored with a periodicity in mind, such that they can act as mirrors to different types of wavelengths of light, and it will have an irregularity within the periodicity such that it allows for the confinement of light and acts as a cavity. There are different types of photonic crystals as well that come in different dimensions. As we see on the bottom, there's one-dimensional, two-dimensional, and three-dimensional examples of photonic crystals. I will be designing one-dimensional photonic crystals, and we see on the top right an example of another linear photonic crystal, which demonstrates the different qualities that we have to keep in mind when designing them. In particular, the new thing that is shown here is tapering, in which we taper the radii of the bored holes as well as the spacing between the holes. And the reason for this tapering is to basically ease the effective index of refraction from the component with the mirror holes in them to the cavity component. And this reduces the loss of the desired wavelength of light when being confined within the photonic crystal. The trade-off, however, for this higher potential is that for the previous photonic cavity, the cavity itself was adjustable during experimentation. However, for photonic crystals, once manufactured, there is no simple way to adjust them. Hence the usefulness of simulations to design these photonic crystals before manufacturing them. For these simulations, we decided to go with the open source package MEEP, which is available in Python. MEEP uses what's known as the finite difference time domain method for computing the propagation of light within semiconductive materials. And what that basically means is it takes time and space and divides them into small sections, so that when given a structure and sources to propagate, that it will divide the structure into very small pieces and will propagate light within the structure and discrete time steps. One of the nice things about MEEP that it's extremely controllable and customizable. However, that's also an issue in part that everything is created by the user. The most important class within this distribution is the simulation class, which handles the setup of the simulation. In particular, the issue that arises here is that it's going to take a lot of different trials and errors to create the best designed photonic crystal. The simulation class is dependent on taking a list of geometric objects, all of which have independent properties of location and dimensions. An example of the issue with this is, let's say I wanted to increase the spacing between the mirror holes. This may affect the symmetry of the photonic crystal, which is really important for it being able to confine light. In addition to that, it would also create issues with the tapering effect, which will also reduce the quality factor. To automate this process and make it much simpler to be able to iterate through different designs quickly, I made two Python classes. One is the Lagrange polynomial interpolation class, which is used for the tapering purposes and we'll interpolate a function based on some given inputs to allow for any number of holes that follow the tapering function instead of having to manually input the different values. And the other class is the linear photonic crystal class, which allows for automatic construction of geometry and execution of the simulation to find the Q factor. So a quick overview of how the Lagrange polynomials work is that basically if you're given n points, you can plug them into that formula right there and it will create a function of highest power x to the n minus 1 in which it will interpolate and intersect between all the given points. As an example of this working, we see that if we plug the x from any of the nodes into the formula, that will just end up with the corresponding y value. It was mentioned in a paper that instead of using linear interpolation, one group was able to use quadratic and get good results. Thus, this is particularly useful in exploring the effectiveness of nonlinear taperings. Here's an example of interpolation created using 3 points, and we see that a quadratic is formed. So the class that I created that handles the creation and simulation of the photonic crystals takes in a total of 11 parameters. The parameters are given here, in which the order that they are listed is where they take priority in the creation of the geometry. Most of these are self-explanatory. The ones that will require explanation is the 4th one and the last 4. And so what those entail is if use cavity is true, then we will use the input for the width of the cavity, summed with twice the minimum radii, and use that as the minimum spacing for our interpolation function, such that it will allow us to ease the effective index of refraction in the cavity better, such that it will allow for the smoothest possible transmission from the effective index of refraction between the mirror sections and the cavity section, which will improve the performance and lead to a higher quality factor. When looking at the example, this is the reason why the spacing interpolating plot shows 5 spacing index numbers, when in reality we only have 4 holes that are within the taper. Also, it should be noted that the 0 index number represents the standard sizings for the mirror holes. And so the benefits of this, as mentioned before, is that once you create this structure, if you want to make any adjustments, all that is needed is to call a class method, and the structures will be automatically updated while still maintaining the symmetry. That's what I have done so far. If I had more allotted time, this is what I would be doing next. The first step would be to add an optimization feature in which I do some sort of search algorithm to find optimal parameters which maximize the Q factor. My idea was to do parametric sweeps across different parameters, but I wasn't sure what sort of practices were common within this type of searching, and I couldn't find anything. So I came up with an incomplete concept of something to try out and see if it works. So to begin my explanation of my idea, assume that there's only one parameter for our function and that we choose to try 9 locations to search at, such that we result in the array below with 9 different Q factors. Now let's say we want to split this into 2 evenly sized sections. The sections then will consist of Q1 to Q5 and Q5 to Q9, each containing 5 measurements. Then we would in some fashion compare those 2 sections and choose one to increase the searching density within it. We then repeat this process until we hit some user-defined limit and take that as the optimal Q factor of parameters. However, we need to be cautious if the optimal range is near the center, which is the purpose of the subsection between the yellow Qs. We will compare subsections in addition to the normal sections to make sure that we are searching effectively. And through some math derivations, we see that a formula arises for how many nodes we need in each iteration step based on S and alpha. And the last thing that I would do if I had more time would be to create a standalone desktop app, because MEEP is only available for Unix-based systems, meaning it's not available to natively run on Windows. But if you make it into an app, then it not only does it allow for more simplicity for the user only to have to input a certain amount of numbers, but would also allow it to run on Windows without having to dual boot or use a VirtualBox to run MEEP. Here are my references that I used for the presentation, and I would like to thank you all for listening to my presentation.